Hi, welcome to the dynamics tutorials. So for this problem we're going to use Newton's equations, or the equations of motion, again with rectangular coordinates. And this is a kinetics problem, so we're going to be looking at accelerations caused by forces. So for this problem we have a block that has an initial velocity of 10 meters per second. It's 0.6 meters away from contacting a spring. The spring is unstretched or uncompressed, and so it's going, and it has a coefficient of kinetic friction of 0.1. So the block's going to slow down slightly before it hits the spring, and then the spring will compress until the block is momentarily stopped. So we want to find the speed at which it strikes the spring, and then we want to find how far the spring compresses before the block momentarily stops. So we always want to start with a free body diagram, and now we have two different conditions that we're looking at. So one would be prior to hitting the spring. So we have the box, we have its weight, we have the normal force, and then we have the frictional force going opposite the direction of motion. We can do sum of forces in y is equal to 0 because it's not moving down into the plane or moving up off the plane. And that gives us the negative 98.1 for the weight plus the normal force is equal to 0. And so the normal force is 98.1. Plug that into the equation for friction, and then we get that the friction is 0.1 times the normal force, or 9.81 newtons. And then we can do our sum of forces in the x is equal to our mass times our acceleration in the x. So we'll have our frictional force, and that's really our only force in the x during this initial part of the motion. So that's equal to 10 kilograms times ax, and then we can solve for ax, and we get negative 9.81 meters per second squared. Because that's constant, then we can go ahead and use the integrated expressions. So we can look at v is equal to v naught plus act. So that would combine velocity, acceleration, and time. We've got velocity and acceleration that we're looking at, but we don't have time in there. So this one would not be a good choice. Let's think about another one that involves velocity and acceleration. V squared is equal to v naught squared plus 2 ac s minus s naught. That one would be appropriate to use because that one's combining the distance, which we have the 0.6 meters, with the velocity and the acceleration. So let's use that one. We'll plug in the initial velocity, we'll plug in 2 times our acceleration, and then our distance of 0.6. When you're using this one, make sure that you take the square root if you're solving for velocity, and you'll get a velocity of 9.94 meters per second, and it should still be going in that direction. Then we'll draw our free body diagram for once it contacts the spring. So we still have friction, we still have the weight, we still have the normal force, but now we have the frictional force. Remember that the force on a spring obeys Hooke's law, so it's going to be the spring constant K, which we were given here, times the stretch or compression in the spring. And let's use X for that compression in the spring. So we'll do our sum of forces, and the X is equal to 0. We'll have our frictional force, our spring force, both are going in the negative x direction. That's equal to the mass times ax. And we can solve for ax, and we see that ax depends on x, so ax is not constant. So now we have to go back, and we can't use this equation. We've got to go back to the differential equation, but we're still combining a distance, an acceleration, and a velocity. So we're just going to use the differential equation form of this guy here. So this will be ax times dx is equal to v dv, or you might be more familiar with it as a ds is equal to v dv. Because we already had seconds in here, I'm just going to use the variable x so that we don't have s for seconds and s for position. We'll plug in what we have, and then we'll integrate this from 0 compression to the compression at x. And then we'll integrate this from our initial velocity, which is now the velocity at which it hits the spring, to our final velocity, which is going to be 0. So we plug this in, plug in our final velocity of 0, plug in our initial velocity here. Oops, I forgot the square. And then we just group the terms around, and you see that it's a quadratic equation. Whoops, one more mistake here. Quadratic equation in x, and so you can use the quadratic formula and solve for x, and you get x is equal to 0.443 meters. And you'll get also a negative root from the quadratic formula, but that negative root has no physical significance. Thanks for watching.